Section 1.3, Strategies for Problem Solving. In this section, we're going to look at a few different types of word problems. The first question is, there are 1,280 students at Toby Johnson Middle School. There are 30 more boys than girls. How many boys are there? There's a couple different ways we could approach this problem. We could definitely do it using algebra. This is not an algebra class, so that's not going to be my main focus. We're going to focus on this method called guess and check. So my suggestion, unless you are just already really good at algebra, because I'm not really here to teach you algebra in this class, my suggestion is most of the time we're going to do guess and check. So we'll focus on this. I'll briefly mention something about this in a few minutes. What do I mean by guess and check? Well, I don't know how many boys there are. I don't know how many girls there are. I do know that there are 30 more boys than girls, and I know that the boys and girls are supposed to add up to 1,280. So I would start some sort of a chart here. How many girls go to the school? How many boys go to the school? What's the total number of students at the school? Some sort of a chart like that. It doesn't have to look exactly like this. I didn't have to put girls first, for example. But some sort of a chart where we can start guessing at answers and see if it works, see if it makes these both true. Some sort of combination of girls and boys that would make both of these true. So here would be my suggestion on how to do this. Just pick a random number and put it here. Right? Like how many girls go to the school? I don't know. There's 1,200 something total. Maybe we just make a guess. It's okay if you don't get it right. You're not supposed to get it right the first time. That kind of defeats the purpose of guess and check. Just put a number there. Now, I know we have 30 more boys than we have girls. So if I really did have 600 girls, understand that would mean we have 630 boys. Because of what it says right there. But also it says the total is supposed to be 1,280. Do those add up to 1,280? No, but it's close. That adds up to 1,230. Okay, so we're close, but it's not what we need. So we make another guess. And you should think to yourself, well, should I guess at more girls or less girls? Well, more girls would also mean more boys, which would get this total up. So I think we need a bigger number than 600. Okay. Maybe, I don't know, let's say 650. You could guess at 700, you could guess at 800, you could guess at 612. Just guess bigger than 600 because we know this is too small, right? We know it's supposed to be 1,280, so that's too small. We need more people. Okay. There's no particular reason why I put 650 here. I'm just trying to get something bigger than that. If there were 650 girls, how many boys would there be? Well, remember, there has to be 30 more boys, so there would have to be 680 boys. Does that total up to what we need it to total up to? 650 girls plus 680 boys. I think we're too much now. I think we're too big, right? Go ahead and add 650 and 680. I think you get 1,330. So now we're too big, right? But here's what's good. We know this guess was too small. We know this guess was too big. So that means your next guess should be somewhere in between. So guess at anything in between 600 and 650. You could guess at 610, 620, 649. Anything between 600 and 650 would be a reasonable guess. Um, I'm going to go ahead and kind of go in the middle here with 625. If there was 625 girls, how many boys would there be? Think there would be 655 boys because there has to be 30 more, right? So 625 girls plus 655 boys. Let's see what happens there. I think that actually works, right? I think that actually does make what we wanted it to make. So that checks out. Okay. Now remember the question said how many boys are there? So this is my final answer right here. Okay. Uh, don't think it's always going to only take you 3 tries. It definitely could take you several more than that. But this is how the process works. This is a process called guess and check. That's the one I'm going to focus on. If you really remember your algebra, maybe from some other class, people might set up something like this. Boys plus girls equals 1,280. And the number of boys equals to girls plus 30. And that's something called a system of equations right there. If you know how to solve a system of equations using, for example, the substitution method or the elimination method, go for it. You're welcome to do that. But again, we don't do much algebra in this class, and so I'm not going to focus on that approach. But I'm totally fine if you do know how to do something with this and you want to solve it that way, you will get the same answer. But I think most of us are going to be solving it this way for this class. Okay, next question. Number of apes and beetles in a room total 30. Number of apes and beetles in a room total 30. The total number of legs among them is 116. Determine how many apes are in the room. So just living your life, your typical day, you come across a room, you notice, hey, there's a bunch of apes and beetles in there. I think there's 30 of the things total, right? And then you just count the legs and you say, hey, there's 116 legs. How many apes must be in that room? That's what the question's asking. Now, of course, for this problem, we need to know how many legs these animals have. I think we probably already know 2 legs there. I'm going to tell you that a beetle has 6 legs. If this was a test question, of course, I would probably let you know that information. I wouldn't necessarily expect you to know things like that. So if this was a test question, don't worry, you'd probably be told how many legs these things have each. Let's guess and check our way to the answer. I don't know how many apes are here. I don't know how many apes are in the room. I also don't know how many beetles are in the room. Uh, we would like to check something about the total number of legs. So that will probably kind of be my check column over here. But I would probably set up some sort of a table like this. Okay. How many apes do we have in the room? How many beetles do we have in the room? I don't know. What if we just guessed at 20? Pick a number, right? I mean, pick a number less than 30, of course, but pick a number. Okay. Now, if there were 20 apes, again, that's just a random pick. It's just a random guess. Probably not going to be correct on the first try, and that's okay. You're probably not going to be correct on the second or third try, and that's okay. If there were 20 apes in the room, how many beetles would need to be in that room? Remember, they're supposed to add up to 30. In the previous question, I was adding 30 to this to get my next column, but I need them to add up to 30. I need to actually do 30, take away 20, and say, well, I guess there's 10 beetles, right? 20 plus 10 totals to 30. Now, if there were 20 apes and 10 beetles, would that make the legs be what we need it to be? Because we need that to be 116. Well, remember each ape, there's 20 apes and each one has 2 legs. So that's the total number of ape legs we got in the room. There's supposedly 10 beetles in this scenario, and each of those has 6 legs. So that's the number of beetle legs we got in the room. That's that's 40 ape legs plus 60 beetle legs. That's 100 legs. We need 116. We need more legs, right? We need more legs. So how are we going to get more legs? Well, I think what a lot of people would do is try to make this number bigger. They say, I need this number bigger, so let's increase this, right? And in the previous problem, that is exactly what we did. But this problem's a little different. In the previous problem, it said something about the number of boys is always 30 more than the number of girls. So if I increase the number of girls, I'm also increasing the number of boys. That's not how this problem works. If I think about this, if I increase the number of apes, this is actually going to have to go down because they have to add up to 30. If I put like 25 apes, now I only got like 5 beetles, right? They have to add up to 30. And think about that. The beetles are the ones with a lot of legs. If I want more legs, I actually need more beetles in the room, not more apes in the room. I actually need less apes and more beetles to make my legs get bigger. I'm going to lower this number, this guess. Let's say 12. What if there were 12 apes in the room? Again, I'm just making a guess that's less than 20. Why am I going down? Because if this number goes down, that will force this number to go up. And if the number of beetles increases, the number of legs is going to increase because the beetles are the ones that have a lot of legs. So if there were 12 apes, that would mean there would have to be 18 beetles. They have to total up to 30. 12 plus 18. If there were 12 apes, remember each ape has 2 legs. And if there were 18 beetles, each beetle has 6 legs. That means we have 24 ape legs, and 18 times 6 is 108 beetle legs. 24 ape legs, 108 beetle legs. That adds up to 132. We're actually too big now. We had too small amount of legs here, and now we have too many legs. So we know my answer for apes at least is somewhere between these two. Okay. Again, I'm going to guess somewhere between 20 and 12. Anything would make sense between 20 and 12. I'm going to go with 16. And and remember, I know the answer already. So that's probably why I'm getting it, probably on the third try here. When you're doing this on your own, you probably are going to take more guesses than this. Okay. If I did have 16 apes, there would have to be then 14 beetles. 16, 30 take away 16. If I did have 16 apes, remember each ape has 2 legs. That's how many ape legs there are. If I did have 14 beetles, remember each beetle has 6 legs. That's how many beetle legs there are. 16 times 2 is 32. 14 times 6 is 84. Go ahead and add those up and see what you get. I think we actually get 116, which is what we were trying to get. That's what we wanted. That checks out. Don't forget to answer the question. The question was, how many apes are in the room? This is my answer. 16 apes. If you prefer or understand algebra, you are welcome to do this. I would do something like this. Apes plus beetles total up to 30. Apes times 2 would be your number of ape legs, and beetles times 6 would be your number of beetle legs, and that's supposed to add up to 116. And now we have what we call a system of equations. You can solve for A, you can solve for B using substitution or elimination. That is not what I'm focusing on in this class. But again, if you know this process already, you are welcome to do it. Most of you are going to use the guess and check process. Next question. On the first 2 exams, Shelby scored 82 and 66. In the first 2 exams, Shelby scored an 82 and a 66. What score does Shelby need on the 3rd exam to raise her average to 80? You know how to average numbers, right? Like if we just focused on her first 2, I would go 82 plus 66, and I would divide that by 2 because we took 2 tests. So at the moment, Shelby has a 74 average, right? At the moment, when she just took those first 2 tests, her test average is 74. But she wants to do better. She wants her average to go up to an 80. So if she's going to go take a 3rd test, what score does she need to get on that 3rd test to make her average 80? Because right now her average is 74. You average 2 numbers by adding them up and dividing by 2. You average 3 numbers by adding them up and dividing by 3, and so on. Just a reminder, my suggestion while you're watching these videos is to hit pause at a time like this and try to go figure it out, right? I'm not going to pause. You can pause. You can turn the video back on when you're ready. I'm going to keep going, but I think it's a good idea, instead of just watching me do the problem, for you to try it first and see if you can come up with the answer. I'm gonna keep going here though. I'm guessing at Shelby's score on her 3rd exam, right? This is going to be my guess. And then my check will be something about the average on the 3 exams. We're hoping to make that be 80. I would set up something like this myself. It's going to be her score on the 3rd exam. I really don't know. What if she scored an 85 on the 3rd exam? This is just a guess. I do not know. Actually, I do know, but in general, we don't know usually, right? I wrote the problem, of course I know. But I'm pretending I don't know. I'm guessing at 85. What would be her average on the 3 exams if she scored an 85 on the third one? Well, she already got those 2 scores, so we're going to have to add that plus that and divide by 3. Let's see what happens. 82 was her first exam score, 66 was her next one. We're saying maybe 85 was the third one. Add them up and divide by 3. That's how you average 3 numbers. Get on your calculator, add those up. That's 233 divided by 3. Not a super nice answer, but it's about 77.7. I'm gonna round that off to about 77.7. I know that says 77.6, but look at the next number right after that first 6. Remember, if it's 5 or more, we have to round up. If the second number after the place we were rounding off to was less than 5, we would leave it alone. We would call it 77.6. But that next number after that 6 is another 6, and that means I'm rounding up to 77.7. That's not what we need. That's close to what we need, but that's not what we need. I need this to go higher. I need my average to be higher. So making your average higher means doing better. Do better on your test if you want your average to be higher. Maybe she did a lot better. Maybe she got a 95 on that next test. We just need to guess at something bigger than 85. Maybe she got a 95 on that next test. Maybe she got an 82 on the first one and a 66 on the second one. And we're saying maybe she got a 95 on the third one. The average of those 3 numbers I could get by adding them up and dividing by 3. Go ahead and add them up. You get 243 and then divide that by 3. And this time I get a nice number. I get exactly 81. Add them up, divide by 3, 81. So we're very, very close, right? We want it to be 80. That one says 81. So we're super close here. This guess gave us too low of an average. This guess gave us too high of an average. So we need to make our next guess be somewhere in between. That could be 86 or 87 or 88 or whatever, anything in between, all the way up to 94. Okay, remember, I'm going to get the answer probably on this one just because I know the answer, but in general, we probably don't. So you may need to take, more than 3 guesses before you get it. You may take 10 guesses sometimes before you get it. So don't get frustrated if you're not getting it fast. You're probably not usually going to get it as fast as I am here. Seems like I'm usually getting on the 3rd try. 82 plus 66 plus 92 divided by 3. That would be her exam average if that were the case. 82 plus 66 plus 92, that adds up to 240. Go ahead and divide 240 by 3. You actually get 80, which is exactly what we were trying to get. So what score does she need on that 3rd exam? I think she needs a 92. Because that created the correct average that we were looking for. Again, that's how most people in this class are going to do this problem. That's how I'm going to focus on is guess and check. This is not an algebra class. We actually do very little algebra in this class. This just happens to be one day where it could pop up if you wanted to do that. If we were going to be doing algebra, constantly all the time in all the sections, then of course I would be teaching you this way. But This is just one of just probably a couple days in the whole semester where we're going to even see algebra pop up at all. So I'm focusing on guess and check here. What would the algebra look like? I would probably say, well, 82 is what she got on the first test. 66 is what she got on the second test. We don't know what she got on the third test, so we would call that something like X. I would add those three test scores up and divide by 3, and I would hope to get an answer of 80. We would have to solve that for X if we wanted to do this algebraically. This is not a system of equations. This is just a single equation. A system of equations is where you have more than one equation and usually more than one variable. So some of you might know how to solve that, and I'm okay with that. If you understand how to solve that problem and you'd rather do it this way instead of this way, there's not a problem with me. I'm just not going to focus on, I'm not going to do this. I'll let you work on that if you feel you want to. Otherwise, I think you should do it this way. Okay, next question. Determine the units digit of the counting number represented by the exponential expression 19 to the power of 768. What do they mean by units digit? They mean the ones place. That's what they mean by the units digit, the ones digit. The number on the far right. If it's a whole number, the number on the far right is the units digit or the ones place. It's a weird question. What's 19 to the power of 768? That means 19 times 19 times 19 times 19, 768 times I would have to say that. It's a really big number. And we're not asking for the answer to this. We're not being asked for the answer to this. We're just being asked in that really big number, what digit comes at the end? What digit comes in the ones place at the very end? I mean, I allow you to use your calculator. What if I just took 19 to the power of 768? 19. Now on my calculator, I have a button right here that raises to a power. So I would say raised to the 768, and it would look like that. You might have a button like that on your calculator to do exponents, but you also might not. There's several different buttons that people have on their calculator that gets them into the exponent, into the power. Since I don't know what kind of calculator each one of you have at the moment, if you don't know how to do this on your calculator, you should pause right now and you should go Google something like put the title of your calculator and also how do I do exponents? How do I do exponents on whatever your title of your calculator is? And I guarantee you'll find it. Probably you might need to watch a quick video and they'll teach you how to do exponents. That's something that you should do. That's something you need to know for this class is how to do exponents on your calculator. Go ahead and do that and come back if you need to. If you already know how to do exponents, let's keep going here. The problem with just doing 19 to the power of 768 is your calculator is probably going to say, no, I'm not doing that one. I'll do a lot for you. Not doing that. Too much work. The answer is too big. Even your calculator can't figure this one out. Gave me an error. Calculation exceeds the range of values this machine is able to display. It's so big the calculator can't even handle this. So you're saying if the calculator can't handle it, how am I supposed to do this problem? How do you expect me to figure out the answer if the calculator can't even do it? Remember though, I'm not asking for the whole answer. I'm just asking for the last digit in the answer. I'm just asking for the ones place. And also remember earlier in this class, in one of some of the earlier sections, we've been looking a lot at patterns and talking about can we figure out a pattern and answer questions that way by looking at a pattern. And I think I want to do that. What if I look at some other powers of 19, like ones that our calculator probably can handle? Like 19 to the power of 1. We shouldn't really need a calculator for 19 to the power of 1, but it's 19. 19 to the power of 2. What does that mean? That means 19 times 19. That's 361. 19 to the power of 3. That's 19 times 19 times 19. That's 6,859. Let me just go ahead and write down some of the next ones. 130321. 2476,099. 47045881. And let me just pause for a second. Remember, I'm not really interested in the whole entire answer to this. I'm just interested in what is in the ones place. What digit is in the ones place? Well, this has a 1 in the ones place right there. This has a 9 in the ones place. This has a 1 in the ones place. This has a 9 in the ones place. Do you see some sort of a pattern happening right there? Do you see some sort of a pattern? 919191. That's what it looks like to me. 919191. It looks like we found a pattern, right? And maybe we can use that pattern to help answer this question that we're really trying to get to. Just because that pattern worked on the first six doesn't necessarily mean it's going to work forever. If you're not convinced, maybe do some more. Do 19 to the 7, 19 to the 8, 19 to the 9, 19 to the 10. Do some more. Remember, we learned earlier in this section about inductive reasoning. That's exactly what we're using here. Looking at examples to try to conclude something specific. When we use inductive reasoning, we're never 100% sure that we're right, but the more examples you look at, you probably would convince yourself, yeah, I think it does go 919191 forever. And even more than that, notice that all the odd powers have a 9 at the end. Notice that if we raise 19 to an odd number, it seems to always end in a 9. 19 to the first power ends in a 9. 19 to the third power ends in a 9. 19 to the fifth power ends in a 9. It also looks like if I take 19 to an even number power, those seem to always end in a 1. 19 to the second ends in a 1. 19 to the fourth ends in a 1. 19 to the sixth ends in a 1. If we believe that pattern, we're kind of done here because that's an even number. 768 is an even number. It should end in a 1. So looking at patterns helps us do something that we can't even do. Our calculator can't even do that. If we tried to sit there and actually multiply by hand 19 times 19 times 19 times 19 that many times, that would take forever. But we're pretty sure, based off of what seems to be happening with patterns, we're pretty sure But it's always going to end in either a 9 or a 1. And also, more than that, depends on if the power is odd or even. That's an even power. It should follow like all the other even powers, and it should end in a 1. That's our answer based off of the pattern that we see. Let's do another one like that. That might be a little bit harder than this previous one. So same idea, determine the units digit or the ones digit of the counting number represented by the exponential expression 7 to the power of 1,145. I mean, same deal. I would probably suggest just sticking it in your calculator first and hoping that it works, but it's not going to work. You might get lucky and maybe it'll just tell you the answer and you just pick out the ones place and you're done, but probably not going to work on your calculator if I give you a problem like this, because the whole point is trying to do it by finding patterns. So my suggestion is to look at some powers of 7 and see if we can find a pattern in the ones place. Remember, that's just the number on the far right in your answer. Well, 7 to the first power, of course, is 7. 7 to the second power, that means 7 times 7, that's 49. 7 to the third power means 7 times 7 times 7, that's 343. 7 to the fourth power is 7 times 7 times 7 times 7, that's 2,401. This one's a little bit more difficult because I don't really see a pattern yet. Remember, we're just looking at the ones place, but 7931, there's no pattern there. There's no pattern happening yet. Let's do some more, see what happens. What if I took 7 to the power of 5? 16,807. What if I took 7 to the power of 6? 117,649. What if I took 7 to the power of 7? 823,543. 7 to the power of 8. 5764801. Do we see a pattern now? Look at the last digit. 7931. 7931, 7931, 7931, 7931. Maybe there is a pattern. It's just more difficult than the previous question. Maybe there is a pattern, but maybe it goes in groups of 4 before it starts repeating itself. Is it going to continue to be 7931? Probably. You may want to check some more. I'll leave that to you if you want to check another group of 4, like 7 to the 9, 7 to the 10, 7 to the 11, 7 to the 12. I think you're going to find it's another set of 7931. So what does that mean? It means my answer to the question I'm really trying to answer is either a 7 or a 9 or a 3 or a 1. It's just which one is it gonna fall under? Is it gonna end in a 7 or a 9 or a 3 or a 1? It has to be one of those 4 answers, probably, is what we're seeing from the pattern here. But this one's harder because the last question was just, we could just say odd or even. There's only 2 things it was ending in. We just looked at the power and decided if it was odd or even because it was just multiplying, I'm sorry, alternating between, odd power, even power ended in different things, but that's not what's happening exactly here. These are going in groups of 4 before they start repeating. Right? This is a group of 4. This is a group of 4. So here's what I want to do. When you have a group of 4, or I guess a group of something bigger than 2, you should take this power, take that power that we're looking at and divide it by 4. Why am I dividing it by 4? Because that's what the groups are going by, groups of 4. It's a harder problem than the last one. The last one was only going in groups of 2 and then it repeated itself already. I guess what I'm saying here is if you notice, if you're doing a problem like this and you notice it's going longer than groups of 2, whatever it's going in, like 4, for example, divide that by 4. Here's what I mean. Do long division. Take that power and divide it by 4. Got to know how to do long division. 4 goes into 11 twice. 2 times 4 is 8. 11 minus 8 is 3. Bring down that 4. If you don't know how to do long division, you should pause the video and go Google up a video on how do I do long division and remind yourself, because I know you knew at one point, maybe you forgot. 4 goes into 34. How many times? 4 times 8 gets you as close as you can to 34. Subtract, we get a 2. Bring down that 5. 4 goes into 25. How many times? 4 times 6 gets you to 24. That's as close as you're going to get without going over. You got a remainder of 1. And here's what you're going to do with that remainder. You take that remainder and you match that remainder with the power. Remainder of 1, I'm going to a power of 1. And my answer is 7. If I got a remainder of 2, I would go up to a power of 2, and I would say my answer is 9. If I got a remainder of 3, I would go up to a power of 3, and I would say my answer is 3. But I got a remainder of 1, I'm going up to a power of 1. I'd say my answer is 7. That's our best answer based off of the pattern that we are seeing. So that's definitely more difficult than the previous question. Moving on to our last set of problems, we're going to look at a few problems that have to do with handshakes. First one, I think we got about 3 more questions left. First one says there are 5 people in a room. Everyone shakes hands with each other. How many total handshakes are there? You got 5 people in a room. Everyone basically introduces themselves to each other by shaking hands with all the rest of the people. How many total handshakes are there? You should pause right now and you should go take a couple minutes and try to come up with an answer and then come back and see how we do. I'm going to continue here. If there are 5 people in a room, I see different answers. When I ask this question, sometimes I'll see people say 25, and I think they're saying 25 because 5 times 5, right? I say, well, 5 people in a room, I guess I'm going to shake 5 hands. If I'm one of the people in that room, I guess I'm going to shake 5 hands. So 5 people, 5 hands, 5 times 5. That's why I think people say 25 sometimes. It's not the right answer, partly because you don't need to shake your own hand, right? You're not going to shake 5 hands in the room. You're only going to actually shake 4 other people's hands. You would look weird standing there shaking your own hand. Like all those other people would be like, what is this guy doing? So if you're a person in that room, you're actually only going to shake 4. Some people do 5 times 4 and they tell me the answer is 20. And that's a reasonable guess. It's wrong, but it's a reasonable guess. I understand how you could come up with 20 because you say, if I'm one of the people in the room, I'm going to shake 4 hands and everybody's going to shake 4 hands. So 5 times 4 is 20. What's wrong with 20? You're double counting some handshake. You're double counting every single handshake. If you're going to say the answer is 20, you actually double counted everything. Let me show you what I'm talking about. So 20 is not the right answer either. It's actually half of 20 because 20 is double counting. Let's say we have these people here. 1, 2, 3. Those are 5 different people represented right there. If I'm this first person, I'm going to go shake 1, 2, 3, 4 hands. I'm going to shake 4 hands right there. If I'm this person, how many hands am I going to go shake? I don't want to say 4 right now because I already did one of them. I don't need to do that one again. So I don't want to do another 4. I just want to say 3. This person has to shake that hand and that hand and this hand over here. That person actually only has to do 3 because they already did that one. Why would we do that one again? And then look at this person. How many hands shakes is that person about to go do right now? Well, not 4 because they already did that one and they already did that one. Like, they don't need to repeat this one. They don't need to repeat that one. They actually only need to go do 1, 2 more. And this person right here, like, they don't need to repeat this handshake. They don't need to repeat that handshake. They don't need to repeat that handshake. They really just need to go do that one right there. And now we're finished because this person didn't really have to go anywhere. Like, everybody already came to this person and shook their hand. The answer is 4 plus 3 plus 2 plus 1. The correct answer is 10. That's one way to look at it. If there are 5 people in a room, 4 plus 3 plus 2 plus 1 is going to get you the right answer. But remember, the other thing that I said a few minutes ago is that 20 was double counting. 5 times 4. 5 times 4 is not a bad approach. 5 times 4 is not a bad approach. You just have to realize that's double counting. If you're one of those 5 people, yes, you're going to go shake 4 hands. But if you stick with 5 times 4, you're counting every handshake twice, and we don't need to do that. But if you realize that counts every handshake twice and you just want to cut that in half, that's going to give you 10 also. Both of those are valid ways to reason through this problem. I really don't care which way you do it. Both of those are valid ways. Now, on the next problem, I'm about to do this with 12 people in a room. If there are 12 people in a room, I want you to really focus on how we did this and think about how that would change if there were 12 people in a room instead of 5 people in a room. Because doing it the first way, what would it look like if I change that to 12? What would this look like? And doing it the second way, what would this look like if I change that number to 12? What would this look like? Keep that in mind when I switch pages right here. There are 12 people in a room. Everyone shakes hands with each other. How many total handshakes are there? Go try this problem. Pause the video, try this problem, see what you get. See here for a second. Okay. In the previous question, we did it a couple different ways. I could certainly say, well, if I'm one of the 12 people, I'm going to go shake 11 hands, right? Maybe I'm the first person that starts this process. I go shake the other 11 people's hands. I'm not going to shake my own hand, but I'm going to go shake the other 11 hands. And then the second person, they already shook my hand. They don't need to shake my hand again. They just have to shake the 10 other people's hands in the room. And so on, because the third person doesn't need to shake the first 2. They only need to shake the other 9 hands. And if we're going to do it sort of like we did the first method in the last problem, we would go 11 plus 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. And go ahead and do that. There's nothing wrong with doing that. It's going to get you the right answer. The right answer is 66. Is that the best way to do it? It's one way to do it. But maybe this method isn't the most efficient because what if there were 100 people in a room? Do you really want to sit there and do 99 plus 98 plus 97 plus 96 plus 95 all the way down to one? I don't think so. So maybe the second method is better. The second method was more just a quick multiply and divide by two. Because remember, if you're one of the 12 people in the room, you are going to go shake 11 hands and everybody's going to go shake 11 hands. But if you keep it at 12 times 11, you are double counting if you do that. If you divide it by two, you're going to get the right answer. That's the faster way to do it, I think, because this is 132 divided by 2, and that also gets you to 66. 66 handshakes is the correct answer. Which way do you want to do it? It's up to you, but I think this way is more efficient. I think this way is better. Because once again, what if I had 100 people in the room? What if I had 1,000 people in the room? What if I had 1,000,000 people in the room? This is going to get out of control real fast. But this is always a simple multiply and then a divide by two, and you get the right answer pretty quick. You see patterns in both of them. Again, let me pull up that previous question. Remember when there were 5 people in a room? You could get the correct answer by going 4 plus 3 plus 2 plus 1, or we could do 5 times 4 divided by 2, and they both worked. And 5 is a small enough number that either one of those are pretty reasonable. But it got a little harder with 12 people. We could do that first method or the second method, but the second method's just better, right? The second method's more efficient. So what I want to do for our very last question that we're about to do, what if I change the number of people in the room to something even more general? What if I change the number of people in the room to n people in a room? Now you walk into a room, you're hanging out in a room, your buddy says, "Hey, how many people do you think are in this room?" Kind of look around, you think, "I think there's about n people, maybe about n people in the room." Yeah, it looks like about n people in the room. Well, if there were n people in the room and everyone shook hands with each other, how many total handshakes would there be? Let's try to figure that out. And what we're going to do here is figure it out not using the reasoning we did up top, but using the reasoning we did here, just because it's more efficient. We're going to figure this problem out not using the reasoning we did right here, but using the reasoning we did right here. Look at the pattern. With 5, we did 5 times 4 divided by 2. With 12, we did 12 times 11 divided by 2. So what are we going to do with n people in the room? Well, I'm going to take the number of people in the room. I'm going to multiply by 1 less than that, and I'm going to divide that by 2. And that's going to be the total number of handshakes. In that room with n people. And we just came up with a formula. We just came up with what a lot of books call the handshake formula. And having a formula is really cool because now I could answer it for any number. I could do it quickly for 100 people in a room, or 200 people in a room, or 1,000,000 people in the room. Because we figured out a pattern. We figured out a formula by looking at patterns. We were able to do it for 5. We saw how this worked. It was the number of people in the room times 1 less divided by 2. We were able to do it for 12. It was the number of people in the room times 1 less divided by 2. So using our inductive reasoning, that should continue for any amount of people in the room. If there are n people in a room, we should take the number of people in the room times 1 less divided by 2. And now we have a formula. We will wrap it up now. This brings us to the end of this section. Have a nice day.